Speaker today, Professor Albert Chang. Albert got his PhD from the University of Texas, Austin. He's now a faculty member in the CS department of the University of Houston. Albert is an expert and very prolific, I guess, in the area of real-time systems. He's published extensively in the leading journals and also conferences in the area. Now, in particular, his publication about incremental debugging of real-time systems was a feature article in last year's Artery Transactions on Computers. So today, actually, he will talk to us about that topic, and as a bonus, he will also describe some of his recent work on security for embedded systems. So I give the time to Albert.
Thank you, David. Yeah. Okay, so the first part of the talk and major part of that is I'm going to talk about the debugging and verification of real-time and embedded systems specified in real-time logic, which is a first-order logic extended with the capability to annotate time, absolute time. So first, some preliminary introduction to the work, because I think many of you may not be familiar with real-time logic. Basically, this is a logic that was motivated by basically conventional logics like CTL and other linear time temporal logics cannot model time well, so they are capable of specifying related ordering of events, but not assigning time, absolute time, to these events and actions. So real-time logic was born in the late 80s. Basically, we can specify a system in a behavioral fashion, so we do not need the structural functional description, which allows you to actually build a system. So here we are able to specify the behavior of the system, and that's good enough for most purposes of verification. So an implementation is correct if the SP, the safety, the specification of the system implies the safety assertion. So SP implies SA is a theorem. So that's the objective of verification here. Now, there are three possible cases when you attempt to do this verification. First, SA is a theorem that can be derived from SP. So that's good. The system is safe. The second possibility is SA is not satisfiable with respect to SP. So here you have an engineer or a designer who doesn't know what he or she is doing. So the specification is completely wrong. But most likely, the third case occurs. So the system is safe if additional constraints are added. So you have the negation of the safety assertion satisfiable under certain cases. So this is a situation where you most likely find this technique and the tool implementing this technique to be useful. So even an expert programmer or designer can make a few bugs the first try. So this tool is able to basically identify these problems for you. And here the focus is on the timing properties as opposed to the logical correctness properties. Now, here in this talk, I'm going to introduce an incremental approach for debugging. So what happens if the verification tool tells you that there is a problem in certain areas? So this tool is able to tell you automatically what kind of constraints to add or to modify to make this into a correct specification. And this is the high-level look at this algorithm. So with a timing constraint that I have 15 minutes to look at basically two projects here, I'm not able to talk about the details, but I'll be happy to to discuss some more after the talk. So here you have basically a loop, and we incrementally add new constraint until the system is safe. So SP implies the safety assertion. Okay, specification implying the safety assertion. So basically, okay, in step 3, okay, we are adding this new constraint, and later on we'll discuss a little bit how these constraints are created and how they're actually added to the system. I guess feel free to stop me if you have questions in real time, and I'll be happy to answer that question. So let's look at the details of the approach. Here the satisfiability of, if you go back here, so we are doing this incrementally starting with k equals 1, and k is incremented each time we add a new constraint. And basically we like to check whether this new constraint make the SP, the new SP, closer to the correct specification. Okay, that's what we mean by incremental here. If it's going farther away, obviously we do not like that constraint. So originally, we are doing this systematically, meaning that there's a method, but it requires users' intervention, so users' suggestion to see to tell the system whether this constraint is going the right way. But eventually, we would like to have the system behave autonomously, so that the system can be implemented in a robot, and it can check new plans, and the specification is written in this RTL, real-time logic language. So the satisfiability of the SP at the k+1 step, implying SA at the k+1 step, is expressed incrementally. Okay, from the previous, basically, it's not a theorem. It's what we are going to see if it becomes a theorem. Now we're going to use the counting SAT problem rather than the regular SAT, and the reason is because this allows us to know how far away the SP is from satisfying SA. And the modification of the SP and or SA is going to be useful in this debugging process. And bugs are fixed one at a time until the system is correct. That is why it's not good, to use this tool if your system is completely wrong. It would take a long time to be able to complete the debugging. But most of the people who develop real-time systems are basically experienced in the domain, so more likely you're making a few mistakes rather than a lot of mistakes. So motivations for this. Industrial systems, real systems, are going to have large specification, not something you can feed into a standard conference paper. So it is impractical for a system designer to be able to go through this manually, even if you have a team and with regular software to find this missing constraint. So we need to have a tool to do that, and we call this tool SDRTL, for systematic debugger for real-time logic. So let's look at real-time logic and look at some of the features and syntax of this language. I'm just curious if you have seen or know something about real-time logic. Maybe raise your hand. Okay, only one or two. So okay, so because of the time constraint, I may not be able to go over all the details, but at least I'm going to show you the key features. And the key feature is the occurrence function. Okay, it's we use this add character to indicate that. And basically, this is an assignment of absolute time, integer absolute time, to the instance of a specific event. So for example, this is the 15th time I press the this button here, okay, the arrow button to go to the next slide. So I can say this occurs at time 4:39 and with 20 seconds. So I can do that in this language. Okay? So here you can see the occurrence time of the ith instance of event E is at time t. Okay, so the ith occurrence of event E occurs at time t. So I can write formulas like this embedded in just conventional first-order logic. I can specify here, for example, this is the next instance. Okay, I+1 is the next instance event, next instance of this event E. Okay. Later on, we'll look at a simple example, so you can become familiar with this logic before we go over the algorithm for verification and debugging. There are three types of real-time logic constraints, constants. these are actions. These are schedulable units of work. So if this is a computer system, that means a task, a process, a thread. Okay, that is a schedulable unit of work. But these actions could be real actions. So this could be a robot arm moving from left to right. It could be the railroad crossing gate going up or going down. It could be a valve in a pipe closing or opening. So those are schedulable units of work. Now, events constants are temporal markers, and these are instantaneous. So, external event is indicated by omega. So, for example, I can have an external event of me pressing this arrow button. Okay, that's an external event. So I'm external to this laptop. Start event means the beginning. Okay, it marks the beginning of an action. Or, for example, I have the start event of the gate arm starting to move up or maybe move down. And this down arrow indicates the end event, the stop event of an action. So the gate is completely moved down. So that I can model this interval of time later on. And integers are used for timing constraints, for all the notations of time here. And the reason is because if we have real numbers, there will be a problem. And I'll be happy to discuss the reason why. Okay, so this is an example railroad crossing. So I come from Houston, Texas, and there are lots of railroad crossings, intersection. And in Texas, people drive fast, okay? And sometimes they ignore, signs and traffic light. That's why we install intersection cameras to catch people who run a red light. So here we light the gate. So basically you have cars here. Okay. And we light the gate to be completely moved down before the train, indicated by this darker green rectangle, arrive at the intersection. So here there's a small sensor that detects the approach of a train. So once the train is detected by the sensor, then it sends a signal to the gate controller, which is going to lower the gate. Okay, so we light the gate to be completely down before the train arrives at the crossing, because if not, the car may try to continue, beat the intersection. Okay, car arrives, car moving forward. Okay, the train is coming. So these events are happening simultaneously. We cannot use a regular temporal logic to model this, because typically it uses the interleaving model of computation. Temporal logic was used for concurrent, to model concurrent systems, concurrent processes. But real-time logic allows you to specify all this happening simultaneously or in parallel. Okay, car passes. Okay, the train is coming. Okay, and the gate is down. Okay, gate is down. Okay, so if there are more cars coming, they cannot go through and the train goes through. After the train crosses the crossing, then the gate can start moving up. So that's the scenario we like to specify. It's a very simple system, but it's good for lecture, presentation, discussion. Okay, so gate moves up. And you see this the timing constraint or the timing performance or behavior here. So it takes 45 seconds for the train to reach the crossing from the sensor, and it takes 60 seconds. So there are only a few cars, so it takes 60 seconds for the train to pass. Okay? So now we're going to model this in real-time logic. Okay? So here is what we are going to say. When the train approaches the sensor, a signal will initiate the lowering of the gate, and the gate is moved down to the position within 30 seconds and from being detected by the sensor, because it takes 45 seconds for the train to arrive. So 30 seconds, we have a 15 seconds buffer zone. So the gate will be completely down before the train arrives. So this is specified in real-time logic. Okay, you see, the less than or equal is to because all this real-time logic indicates integer time. So here, train approach is the occurrence time of the train approach, the x occurrence of that x instance, is less than or equal. So that means at or before the start of the gate moving down. So when a change is detected, then the gate is going to start moving down. It could be a little bit later. That's less than or equal. It's going to indicate that. And notice that this is an N. So, and also the down gate. Okay, the end of the down gate is going to occur less than or equal to the time the train approach happens plus 30. Okay, so the 30 is a deadline for basically the occurrence time of the gate completely moving down, and this is captured in this real-time logic statement. Okay, now the gate takes 15 seconds to lower itself, and this comes from the performance of this particular motor, driving this gate from the up to the down position. Okay, so this is considered a delay or computation time. Okay, this is something that again is dependent on the actual gate controller and the gate and the weather. Okay, so this is specified, as you can see, the integer is on the left. Okay, and that usually indicates delay or computation time. And you see down gate here and down gate here, and this is a down arrow and this is up arrow. So we are really relating the two endpoints, the beginning and the end point of the same action, and this tells you the computation time. So very complex system can also be specified. You just have a lot of RTL formulas. Now, the next thing we like to say is if the train needs at least 45 seconds to go from the sensor to the crossing, and the train crossing is completed within 60 seconds from being detected by the sensor, then we are guaranteed that at the start of the train crossing, the gate has moved down, and that the train leaves the crossing within 45 seconds from the time the gate has been completely and has been completely moved down. So this is captured. This is captured by this this statement in RTL. Okay, so you see this is a if this happen, then this is going to happen. Okay. So this is really the safety assertion, and we like to relate this safety assertion with the specification, which will capture here. Okay? A very simple system, but I think it illustrates what we are trying to do here. Questions so far? Okay. So now the class of formulas that are in this format is called path RTL. It's a subclass of RTL, because by now the theorists in the audience will say, okay, this is first order logic is not decidable. So how can we claim to have an efficient solution? But this is only a subclass of the RTL formulas, and for this we can have an efficient solution. Notice that all these statements have basically an occurrence function plus or minus an integer less than or equal to another occurrence function, and they are connected with connectives like AND. And of course, basic logic course will tell you that this imply can be changed, right? So it becomes not the premise or the consequence. So it can be changed to logical connectives other than the implied symbol, right? But you can see, all this, okay, have the occurrence function plus or minus. Here in this case is a 0, integer is 0, less than or equal to another occurrence function. So if your formulas are of this form, then they are called path RTL. And for this, we can come up with a general algorithm. Now, in the worst case, this is still exponential time, and hence, the objective of this talk is to basically push the envelope by saying that, in fact, a lot of these formulas can be analyzed in polynomial time. Okay, so this is the form, as I said, the form of the formulas. Occurrence function plus or minus integer less than or equal to another occurrence function. Now we have analyzed several real systems, including railroad crossing. Well, the system I have is very small, but there could be multiple tracks. Okay, we have analyzed a nuclear reactor, Boeing 77, the airplane integrated airplane information management systems, and also the X-38. This is, in fact, I have a full description of this in the 99 paper and also in my textbook. So just do a little bit advertising here. So I have a textbook that talks about all this and plus more. But obviously, the results here, the main results, it's actually beyond the textbook. It's published more recently.
Can you give us an idea of how large the specification, something like this is?
Sure. Both the Boeing and this system, we're talking about hundreds of formulas. So like 500, 600. The railroad crossing is much smaller. Okay. This one is actually a simplified version. It's about 100 formulas in RTL before conversion to the format we need, which are cross or form, and that has more crosses.
So that's a complete spacecraft is just hundreds of formulas.
That's right. Well, this is not a complete spacecraft. This is only this module. Okay, that integrated airplane information management module. It's only a small subset, I must say, not the entire aircraft. The entire aircraft, you're talking about millions of formulas.
Right.
Okay.
But an interesting part of it.
That's right, exactly. And the part that we can get our hands on, meaning the source code. So as people in academia, as faculty members, we may not be able to get the source code so easily. Especially it's a private companies, and if it's the Defense Department, it's even harder. Okay, so yeah, but even with hundreds of formulas, doing it by hand is impossible, and with conventional model checking, for this kind of thing, it's still too large because there's a time dimension in this problem. Okay, so let's see. Let's look at how we translate these formulas. We need to do some processing before we can actually analyze this using our algorithm. So first, we're going to translate these formulas with the occurrence function into something that's called Pressburger arithmetic. Basically, we are replacing the occurrence function into something that's more mathematical looking, more familiar to you. And for those that have up arrow and down arrow to indicate the start and end time of the action, we use the same function name, but we use 1 and 2 to denote the beginning and the end of these actions. Okay, so that shows that these two functions are related. That shows the endpoints of that action. So that's the SP, and this is the safety property again, translated into Pressburger. Now. Oops. Okay, so we are not going to actually verify this directly. In fact, we are going to prove by contradiction. So we are going to encode the negation of this SP implying SA formula. So not parenthesis SP imply SA. So basically this. And the reason is, if we encode this, then we need to just find one counterexample, and the original formula is proven. Again, this is very basic logic. So you see, I do some, basically, this becomes this, and finally becomes this. So SP and not SA. Okay? So I'm going to encode SP and not SA in a type of graph called a constraint graph. So SP imply SA is a theorem if and only if SP and not SA is unsatisfiable. I'm proving by contradiction. So SP remains the same, but I need to negate the SA. Okay? And negating the SA, again, if you have some logic background, the for all becomes the exist here. So this gives a little bit of problem. So we need to scholemize, use Scholem constant here. So Scholem constant means, okay, this capital T and U means this is for a specific value, not for all. Okay. So this is called a Scholem constant. And this is the form after the negation. Now, some of the less than or equal becomes greater than. And again, we do some simple arithmetic trick. You see the 60 becomes a minus 59 here. So I can use this less than or equal. Because all the formulas have to be written as occurrence function plus or minus an integer less than or equal, okay, for this to work. And the reason is, if we are looking for cycle, a circular path in a graph, okay, I will show you shortly. So again, summarizing, we have original formulas, we get the Pressburger formulas, and then we put into the clausal form like this. Okay. Basically, each clause is a disjunction. Okay. If it's only n, then we write on separate lines. And the objective is to find positive cycles. So I haven't told you about the graph yet, but shortly. Okay, let me go to that. Okay, so this is a graph we want to build. So you create a node for each function. If the function has a Scholen constant, like here f of t, okay, I'm going to create another node. So this is kind of like a more complex graph. It's called a constraint graph. So f of t is a separate node, but it's obviously related to f of lowercase x. So I build a graph like that, and the edge has a weight. And the weight is that integer constant that is in the plus or minus in these formulas. Okay, right here. So you have either plus 45, plus 1, or minus 59. That is the weight. That's the weight on the graph. So you see minus 30, minus 15, 0 here. So now the objective is to find positive cycles in this graph. And let's see if there's any here. Okay, if you don't have positive cycles, that is bad, because we are proving by counterexample. So if you have positive cycle, we are done. If you have no positive cycles, that means you have a bug in your specification. So it's very quick. The problem is if you have a disjunction, then you need to find 2 or more cycles because of the OR. So one could be true, but the cycle could have gone to the other part. But if there are no positive cycle, you have a bug. Okay, so we have avoided using resolution, which is the standard procedure to use on the Pressburger arithmetic formulas. So here, if you identify positive cycles, there's a bug. And in fact, there's a bug here. Okay. So we need to redesign, and the goal is to do this fully automatically, autonomously. Okay. So here is adding some new edges to the graph and new nodes. So this is suggested by the tool. Again, I don't really have time to go into details, but I think you get the idea. And finally, okay, this is telling you how to basically add cycles to the graph, or you transform. Okay, let me go back here. So adding cycles to the graph to create positive cycles, or maybe transforming a negative cycle into a positive one. Okay. That of course will modify existing constraint, or maybe have to create new constraint, new formulas. Okay. So this is how the system works. Obviously, the more you know about the domain, let's say this is for airplane avionics, the better, okay, the tool is going to respond. So it's going to encode domain knowledge. So there's some knowledge-based systems inside. Yeah. Of course, you can just do this blindly. Just search, around the area and see if you get a more correct specification, as I told you earlier. Because with the counting SAT, let's see, let's go back here. With the incremental counting SAT, there's a numerical value that tells you how far away you're from the correct solution, and that's why we're using that. Again, I think I'm going to skip some details here. That's yeah, but you can go ahead.
So it seems to me a problem with this is if you try to fix the specification, there are many ways for you to do that.
That's right.
Right?
Yes.
So among all the possibilities and how you pick
Right.
one that should
You pick the one that has basically the better score. So because for each of these fixes, there's a numerical score that we get from this counting SAT.
and that is from the domain knowledge.
No, that's without domain knowledge. With the domain knowledge, it's even better. So you can say this one has a higher priority, to be added.
Okay. But without domain knowledge, then the score corresponds to what?
Basically, how far away you are from the correct SP implying SA. So let's go back here. So basically this. Because the score would be 0 if you have this. Well, SP implies SA. This is actually a negation. So yeah, basically this. So the score will be 0. So you are there. But the farther away, the more constraint missing, or the more incorrect are your numbers in these timing constraint, there will be a larger number. Okay.
I think
So,
I have the intuitive idea.
yeah, so the goal is to give you an intuitive idea here, not to actually, show all the details. It will take more than an hour just to talk about this part actually. But I encourage you to look at the IEEE transactions paper last July. It gives you a lot of the information here, and there's some other conference papers at RTSS and RTAS, and there are description of the titles in my website, and they are abstract, but the actual link you can get it from IEEE or some of them from ACM, okay, from the digital libraries. Okay, so let's go back. Yeah, there's some related work with incremental techniques, so I'm not claiming we're the first. But they have done this for other models, other languages, like mu calculus, and but not for real-time logic. So this is brand new for real-time logic. And also there's some discussion on the SAT problem and the incremental SAT. And of course, SAT was defined in 1971 by Cook. Okay, so we add, the tool allows us to add basically cycles, positive cycles, or which may be that could be created by adding one edge, or that could be changing some numbers. That could mean changing the constraints, or you may need to add several edges and nodes in order to create one. And as I said, if you have this junction of crosses, you need several cycles, and you need to build a search tree in order to be sure that you have a counterexample, and hence the original formula, the unnegated formula, is what you want. SP imply SA. Okay, so initially, you can obviously do this manually. So here we are proposing, of course, a mechanical tool that eventually can be fully automated. Okay, and here we are working on the specification, not on the actual code. But eventually, we want to do that to actual code or actual communication protocol in networking. Okay, so again, go back to the railroad crossing. And as I just mentioned, you can add new arc, new edges, or you can transform negative cycles. Okay. And the key point is the increment. Okay. So associated with each change, there's a cost. Okay. It's the increment, and of course, the closer it is to the theorem we want to prove SP implies SA, the better. So we'll choose that one. Sometimes there's a tie, or maybe there are too many choices. So we may have to pick at random. The more choices you have that have the same score, the domain expert would definitely help there. Because typically, if you wrote a program, okay, then there's a bug, and the system identifies it, very likely okay, this is what I did. Okay, so I fixed that. So I choose that particular choice. So definitely with the human domain expert, the developer, the tool will run much faster. Okay, so you have maybe the correct constraint much faster. But even if you don't have an expert, eventually, the convergence issue, so far the system converged. That's a question I get when I give talks at other places, is convergence. But so far we have observed that convergence it occurs 100% of the times with the test cases we have. There's some real test cases. We just remove some formulas or maybe change some numbers, and it gets back to the basically the correct specification. And we also created synthetic formulas, and again the tool performs well. But we cannot say 100% sure. So that's another topic in itself, is proving the convergence. So I'm still looking for a student who is very theoretically oriented to tackle that issue. So we have a tool, and I can refer you to a website, and there's a link from my website, so you can actually run this and try it. So it's not like we just have a paper or papers, but you can try this tool, and you can download and try out the examples I have there. And the links is from my website. So this is an actual run of the system. Okay, and it shows this graphically. Okay, here it shows two crosses are missing. Okay, oops, right, and then it adds this crosses and in order to create positive cycles. All right, I think I'm going to skip some details on the choices of some of the parameters and go to the results directly, because I do want to spend some time on security, I think, because a lot of faculty members and students here are working on security, and that's why I added this bonus. Okay, because initially I sent David the verification talk, but I figured out, okay, even though security is not my main research area, lately I have basically some ideas of applying some of this work, real-time logic, into security, in the modeling and verifying security protocols or intrusion detection systems.
In a way, if we can prove the system to be correct, then the security issue is taken care
Oh, that's right. That would be hard, yeah. But that's the ultimate goal, and that's a good setting point if you can sell this to a client and say this is certified, with this. Okay, it's a guarantee. Yeah. Unfortunately, in the real world, there are far more constraints, far more uncertainties that you can model. That's basically the domain of input is infinite. So it's very hard to do that. But eventually we want to do that. Maybe on a certain piece of the protocol or IDS, the certain core of it. Okay, so this view graph just shows you the if you have 1, 2, 3, 4 constraints missing, and the time it takes on just a standard PC, not a supercomputer, to complete this debugging and verification. And this shows the numbers for in seconds for railroad crossing, the reactor, and also the X-38, which is the crew return vehicle for the International Space Station. This is a lifeboat to return astronauts back to Earth in the event of an accident on board, instead of sending a Russian spacecraft to retrieve them, which takes much longer. Okay. All right, so that's actually a prototype of this X-38. Unfortunately, right now this project is put on hold by NASA because of budget reason. So astronauts have to wait for the Russian, or maybe a shuttle launch, which is often delayed, right, to retrieve the astronauts if there are problems. And I think recently they have some, I forgot exactly the issue. It's oxygen or maybe CO2 detected in the capsule. So it could be serious, right? So this is something used to test the system, and we X-38, the part that we analyze is the scheduling part of the avionics. It uses 4-power PC for Byzantine agreement and for redundancy. And this is dropped high up in the air, and then it can return autonomously back to Earth. So this is a high-level view of our tool. So SD RTL is what we have, and then AD is the more advanced version that can basically do it almost automatically. Okay, so it's and then this basically telling you, the old specification and incremental specification, and eventually we want to do this fully autonomously. Okay, future work. We want to basically, as I said, beside the autonomous thing, we are doing optimization. I didn't show it on this slide. And what happens if you have a platform, a processing platform, that is slower than what you already what you have? So can it still, meet this specification? Because if it's slower, then your actions are going to take longer. If you're aware, power-aware computing, if you're familiar with that, if you run your laptop at a slower speed, then it takes longer to show your PowerPoint slides or run your applications. We like to basically combine this technique with scheduling, the scheduling research. Okay, I should acknowledge this is joint work with Stefan Andre and his group at the National University of Singapore, I think NSF, and also the Institute of for Space Systems Operation. And these are some of the references. Okay. Right. Okay, so that concludes the first part of my talk. Next, I'm going to go to the security part of the talk. So any questions about the first part? Okay. So I think I have about 9 minutes and 30 seconds, and I'm going to just tell you a little bit about the issues and the challenges in this area. As I said, this is a brand new area for me too. We just started this late last year, so I don't have a lot of hard results. Okay, but I will tell you an approach that we're going to take based on knowledge or rule-based systems. So let's see. Okay, motivations. These are embedded systems. Your future car may not have a steering wheel, so joysticks. Okay. Patient monitoring in hospital. So this is the space shuttle. So typically in this system, security is becoming important. But typically, people are more concerned with getting the correct result and having it verified for timing correctness and logical correctness. And security is not the main topic there. But I think the more these systems are deployed, I think it's that we need to incorporate certain level of a security mechanism. So I do work also in embedded systems. So this is an Intel board that we have to check out some DBS algorithms that we have developed to basically save power while still meeting the timing constraint. This is a simple fixed wireless sensor network testbed that my student and another colleague in the department have set up. And we have an intrusion detection system running here. And this is really a test bed because one of my students has a sleeping bag underneath. Okay, so yeah. So he's not underneath right now, but there are lots of wiring and power stuff downstairs. He's in the table here. And afterwards he took it out. He said, "That's okay. I show this. It's more funny. It's a test bed, and there's really a bed underneath. Okay, it's sleeping bag. So what we are doing right now is we want to specify this IDS in real-time logic. Okay, so that's one project, and then use the tool to analyze. So here, of course, we're focused on the timing. So from the time an intruder goes in and modify things, or maybe send an incorrect package, we like to bound this response time in detection. So that's one problem. Okay, with respect to this setup. Okay, now a typical real-time system is like this. So you have a system that is being monitored and controlled. Okay, that's T, and the sensor input. And then there's a decision system consisting of hardware and software. State information tells you about what's happening before, and then you have to make a decision. So determine what to do next. It could be changing the temperature setting, so you activate the air conditioner, or it could be opening a valve to let fluids go through in, let's say, in a refinery or a chemical process, or it could be activating an anti-lock brake, right, to avoid skidding. So all of this can be modeled like this. But in reality, there are more in the modern control systems. Okay, so you have a user interface. The UI folks, user interface folks would be working on this. There's networking. So you may have this system in a control area network, or you may have a system that is actually activated remotely, maybe through an internet. That would not be good unless you certify and verify that you have the system safely operating. So you don't want to have a robot arm in another room in Houston, and I'm changing it here, and hacker, gets in and modify this transmission. So, or you have something maybe more closely coupled, like in a car. And then within the control system, you have monitoring, decision making, actuation, and also the target system. So which is shown in this simplified picture. Okay. So what are the issues in an IDS in such a setting? Some of this, of course, in the wireless sensor networks, the nodes may be running on battery. So the first thing, of course, is accuracy. That's well known to you, right? So the IDS should identify null or field false positives, null or field false negatives. But here, timeliness is important. So you don't want to add the IDS and violate the original timing constraint of the application. Okay, so if your sensor is going to detect maybe temperature changes or maybe CO2 in the air, then I don't want to affect that timing. If you add this IDS module to it. Scalability. Can you scale from small to large or vice versa? And power awareness. This is something that has not been thought of much in the security community, and we intend to work on this. How do you get some security, some intrusion detection, without basically violating the real-time constraints that you have? Okay, so one approach we are taking is based on automatic rule-based generation. So I think here there's a group that is working on automata inlining, so you can model the legal and illegal behavior. Because if you want to model everything, that's not possible. If you want to trace all the possible packets being exchanged, all the execution, all the library calls, that's not possible. But here we give another twist. And the reason is I work on rule-based systems for a long time. And we have a polynomial time tool that can tell you whether a system can meet the deadline constraint. So meaning the worst case execution time, it's always less than or equal to the deadline. And we can do this for, again, a large class of systems. Again, the problem is not decidable in general. So the objective here is to automatically generate this rule-based program that represent the legal execution behavior of a given application program in this embedded system. And now, but the tool that I have only tells you the timing. Here we are checking for security. So we need to encode this as timing, basically timing constraint. And we have some experience doing that, but not encoding security, but rather regular safety properties. So we conjecture that we can do this. And our technique to do the analysis fast is using something called semantic analysis. That's why we can avoid the state space, the reachability graph analysis that is needed if you use an automata-based technique. Okay. Now, at runtime, we're going to append new rules to this automatically generated rule set that has the legal behavior represented. And this uses a new program. Now, if these rules are dependent on the current execution sequences, if some of them are becoming illegal or maybe it's from the intruder, then we'll be able to detect it with this technique. Again, this is incremental, so it's more efficient. I think I need to skip an example because I have a minute and a half left. But anyway, this is the form of the rule base. It's a propositional logic-based language. We also have a first-order logic-based language for MRL. EQL is the simple one. But this is enough for our purpose. And we use semantic analysis and based on special forms that we have proven to satisfy certain timing constraint. Okay, so we can have a program like this and analyze using this strategy. Again, using a compositional and incremental approach. So we can analyze a rule-based program, breaking it down into smaller pieces, and then combining the results. Okay, so I just want to conclude the talk. There's a lot of avenues for further research in this area, and I'll be happy to share with you the some of the workshop papers where I have described more details. They are available on my website. And I like to, of course, show you some pictures. Photography is my hobby, so I usually take pictures of my group at conferences. And this is at RTL 2005. Stefan is here from NUS. This is at the Martian Robot Competition at RTSS. Okay. This is at my lab. There's a CS Open House. This is Wayne Wu from Princeton visiting us. Jeanette Wynn, who is now the head of CISE, keynote speaker. And final picture taken recently in my lab with my students. Thank you. Thank you.